So welcome back students to one more session of your atomic structure. So basically I'm a bit not well with the cold, that's the reason I'm taking the class like this. So today we're going to learn about a concept called blackbody radiation, as well as we'll be studying about photoelectric effect. So what actually is blackbody radiation? Suppose when I take an object like this, right? So suppose if you're just sending an incident ray of light. So what happens, there are three possibilities. One, it may absorb the light, first concept. It may reflect the light, reflects the light, or it may also transmit the light. Okay, these are the three options which we have. Fine. So now suppose if I speak about this black body, what actually is this? This is the normal one. If I speak about an ideal black body, right, and now I'm coming to a concept called this. Now what happens is, if I have to define this term, black body is a particular person. What happens is, when you're trying to send different incident rays, like this incident, I'm sending this light ray, this light ray, this one, incident, sending it on all the directions. This is lambda 1, one wavelength, lambda 2, lambda 3, lambda, okay, this is 3, this is 4, this is 5, this is 6. Okay, now if I have to define, black body is a body which absorbs wavelength of all ranges. That's the first important. Let us write the definition. Black body means black body, or a perfect, if I have to say, an ideal black body, if I have to say, ideal black body. What is it? It is a perfect absorber. It's going to absorb wavelength of all the ranges. Perfect absorber. So I told you, isn't it? It absorbs. So this is the first thing. So it's going to absorb all the wavelengths perfectly, or I can also call it as perfect black body. And the radiation which is emitted by such black body, fine, a perfect emitter of radiation also. So perfect absorber, first point. And if I have to say, and perfect emitter. Right, so this is called black body. Now I have two terms. One, it's absorbing, it's emitting. It's absorbing, it is transmitting, emitting. Now, and the radiation of this particular black body is called blackbody radiation. So let us write that term. And the radiation associated. Okay, let me now take this page. Radiation associated with black body is called blackbody radiation. It's called blackbody radiation. So it's called blackbody radiation. Now, what happens is, when I take this particular concept, now I'm going to heat this black body. Now I know it is a perfect absorber and a perfect emitter, isn't it? Right. I'm taking this black body. Now I started heating this one. When you heat, what happens, the temperature starts increasing. Suppose, let us assume this is an iron partition. Okay, right, iron metal. Now when you're heating this iron metal, first, what is the color which you observe? Red. Okay, now this is our VIGOR spectrum, VBIGOR, correct? Right. In this VIGOR spectrum, we very well know here for red, the wavelength is maximum. For violet, I know the frequency is maximum, isn't it? Frequency is maximum. In other way, here frequency is, or mu is minimum. Here wavelength is minimum. Either way, isn't it? Now see, when you're heating iron, first it becomes red hot from here. Then gradually, when you're heating further, this becomes yellow in color. It's going in this direction. It becomes yellow. Now further, when you heat, it turns almost, from yellow color, red, first red, then it becomes yellow, then white, then it becomes almost purple in color. Right, now see the concept. Now what's happening when you heat and black body? Now this is a black body. This black body, when you heat, what will happen? Gradually it goes towards a range where frequency is maximum, wavelength is minimum. It's going in this direction, isn't it? Yes. So what is the concept now? The concept is, whenever you're heating a black body, First important thing. So let us write, on heating black body, what did we observe? We have observed that wavelength of radiation emitted. So that this particular thing, first of all, you should remember that on heating the blackboard means as the temperature increases. That's a concept, isn't it? So what did we see? As the temperature increases, what is decreasing? Wavelength of the radiation emitted. Fine. So wavelength decreases. This is the first important thing. Frequency increases. If you understand this concept, it is very easy. This is the most important thing. How can I show this in the particular graph? Suppose if I draw a temperature, or if I have to draw graph versus wavelength versus intensity. I am drawing this graph, wavelength, which is lambda. I am taking this intensity on the y-axis. Let's see. Now what happens? The same concept I am applying. Now, as the wavelength increases from here, from this point towards this direction, what happens? Yes, initially, just see intensity in this direction. Now, I'm applying the same concept here. Now, temperature is gradually increasing, right? So, it's going on gradually increasing the temperature. You're increasing the temperature at high, and high, and high. It gradually drops down. Okay. Now, let us take one more temperature you're increasing. I'm taking two different ranges. Okay, now let us mark this peak as T1, let us mark this peak as T2. Now what is important here? As a wavelength is increasing, see here, as a wavelength is increasing, or let us write as the intensity is increasing. Either way I can take, isn't it? Now let me take this point as T2 and let me mark this point as T1. Now see here, when the intensity here, that is where the temperature is maximum, the intensity also is maximum. See here, when the temperature is maximum, the intensity or the frequency is also maximum, right? Then drop this one, wavelength down, wavelength is less. Same, when the temperature is maximum, intensity is also maximum. Temperature is maximum, intensity is also maximum. Then when I drop this, wavelength is less, isn't it, in this point? So what is the concept? Concept is, first important thing, remember this for black body. Then come back to the next concept, the same thing with the graph, and keep explaining. If I increase the temperature, or if I increase the temperature or heat the black body, intensity also is maximum, wavelength is less. I'm comparing between these two. So that is how you have to explain the black body radiation. So once again, that which absorbs completely all the wavelength of all the ranges is the black body, and the radiation emitted by the black body is called black body radiation. That's the second concept. And the third concept is this one. As I've shown you in the Vibgeo spectrum. Now after this, let's come back and learn the photoelectric effect. Fine. So basically, when I have to speak about photoelectric effect, let us write the heading first. Photoelectric effect. Fine. Photoelectric effect. So basically, what happens here, if I have to define photoelectric effect, simple concept it is. So the photoelectric effect, first of all, let us assume, so you're taking a metallic piece like this, like just take a metallic piece, drop in, or just take this metallic piece. Now what are you doing? You're trying to send or incident a certain amount of light on this. I'm just trying to make it simpler for you so that's easy for you to write in the exam. Fine. So you're sending an incident ray on this. Let us name this as incident ray. Incident ray. Okay, fine. Now here, this incident ray, this is a form of energy, isn't it? So here energy is equal to E is equal to H nu. Now what happens? This energy or this photon, basically, when it strikes the surface of the metal, let us write this as metal surface. So when this incident ray of certain amount of energy, H nu, when it strikes a metal surface, what does it do? It tries to eject an electron from this. It will try to drag the electron from this. So this is electron. So this electron comes out from the metal surface with certain amount of kinetic energy that is equal to half mv square. Here I have E is equal to H nu, with certain amount of energy it's hitting the metal surface. Here with certain amount of kinetic energy it's getting ejected out. Now let us write the definition. What is the definition of photoelectric effect? Yes, it is the ejection of electron. Ejection of electron from metal surface Okay, ejection of electron from metal surface when light, okay, light is what? In the form of photon, that is packets of energy. When light, let us write that in a bracket, photon of certain frequency. We have not mentioned what is a frequency, isn't it? Of certain frequency is incident or irradiated. We call it as irradiated, means you are sending that ray into this, irradiated on it. This is called photoelectric effect. Now what happens? Let's see what actually has happened in the experimental findings. So according to experimental findings, let us write the experimental values. So experimental findings of photoelectric effect. So this photoelectric effect, basically, first of all, what did we do? I have sent an incident ray, right, of certain frequency. Electron has ejected out. So for the electron to eject out, what was important? First of all, according to experimental setup, electron ejected only when, first important, the electron has to come out, isn't it? Electron, when did it eject? Electron ejected. Ejected means just coming out. When, what is the condition? When light of required frequency, when you just send a light of certain frequency only. So when light of sufficient energy, let us take one example and see. Sufficient energy strikes, then only your metal or the electron strikes the metal surface, then only your metal or the electron ejects out of the surface. So what is this example? If I have to take, for example, if I have to see like the same diagram, if I have to draw. So here I said certain frequency, okay, that amount of frequency, it varies with every metal. So let us write that varies with every metal. Every metal has a different frequency, then only it will come out. That particular minimum frequency which with the electron comes out, I am using the first term, that is called threshold frequency. This is the minimum frequency, or this is the frequency which varies. Threshold frequency, what is it called? It is also called as critical frequency. This threshold frequency is always depend, or it is sometimes it is also called as minimum frequency. Let us write 3 words: minimum or minimal frequency. Let us underline this. Only if this is there, then only electron ejects out. So that threshold frequency or the minimum frequency which is required, right? It's it's always denoted by, if I have to say, it's we also call it as work function. Fine, that h nu naught. Okay, let us write that as h nu naught. This is denoted by h nu naught, which is also denoted by w naught, which is measured in electron volts. So this is the minimum frequency. So if I take a metal surface, suppose let me assume this is a lithium metal. Let us assume one more, this is sodium metal. Let us assume one more, potassium metal. Here I am assuming one more metal, magnesium metal. Here I am assuming one more metal, copper metal. Again I am assuming silver metal. Suppose if I take different, every a metal has a different threshold frequency, I said, and it is also called as work function, W naught. Now for sodium, the W naught value is 2.3. Unless it is 2.3, it will not come out. The electron will not eject out. Suppose if I take the work function of potassium, it is 2.25. If I take the work function of magnesium, it is 3.7. The same thing with lithium. If I take work function is 2.42. Then if I take copper, work function or the required frequency h nu naught value is 4.8. If I take silver, it is 4.3. That means unless until I supply so much of energy, that particular electron is not ejected out. Now what is the next concept? Now I know about threshold frequency, I find. So now with this threshold frequency, now what should I remember? Now when required photon falls on the surface, right? Electron, what happens? Now I'm sending the threshold frequency, required threshold frequency. So let us write with required h nu naught, okay, or w naught. What happens? The electron from this atom, whatever is there, this which is present in the shells, it is ejected out. Okay, electron breaks away, right? And From where? From atom, from this atom, by overcoming, it has to overcome, because proton also drags the electron inside, isn't it? By overcoming nuclear attraction. This is important. It has to overcome all the nuclear attraction, then only it is going to eject out. So if without this nuclear addition, it will not come out of the atom. Now we will write the actual equation for this. So first of all, when I said E is equal to H nu, it is incident on the metal surface. So let us take this H nu. When this H nu strikes this metal surface, every metal has a certain amount of W naught. That W naught is equal to H nu naught, H nu naught. And immediately when this strikes, it ejects the electron out, and this has a kinetic energy of half mv square. So add with half mv square. This is your concept, isn't it? This is most important. This is the equation for photoelectric effect. Now what is this? Nu is the frequency of the incident light. Nu naught is a work function, that is a frequency which differs with every metal. Half mv square is the kinetic energy with which it has come out. Take this half mv square on this side. What do I get? I am going to send this in the other way. H nu naught, H nu minus H nu naught. Now I think I can write this in this direction. See here, y is equal to straight line curve, y is equal to mx plus c. Why? Because when I plot this in the form of a graph, I am plotting kinetic energy here, y-axis I am plotting kinetic energy, that is half mv square. Here on the x-axis, what do I have? I have h nu, isn't it? Yes. Now I get this is a straight line graph, so I get a straight line like this. Now what is the intercept for this? C is the intercept, isn't it? According to this, what is the intercept? H nu naught is the intercept. So I am going to get intercept as, if I take this intercept as H nu naught. That's it. So this is your concept for photoelectric effect. So let us write nu is the frequency of incident radiation. That's the first concept. Incident ray. Nu naught is what? What did we say? Is a threshold frequency. Okay, threshold frequency of it. It varies with different metals. That is important. Okay, right. This is your photoelectric effect concept. Hope the concept is clear. Let's come back and learn one more concept. Right. After the photoelectric effect and blackbody radiation, so let us come to a concept called the dual nature of electromagnetic radiation. So what did photoelectric effect say? It is clearly explained that electromagnetic radiation may consist of small packets of energy, isn't it? That is what we have seen in the concept. So we said electromagnetic radiation. Let us write this word as EMR. What does it contain? It contains small packets of energy, isn't it? What are these small packets of energy called? They're called as quanta. Quanta, right? Many. Quanta means many, like many packets of energy. If you're writing in one particular thing, if you're speaking about one word, then we call it as quantum. Quantum means one packet. This is many small packets together. Right. So these when I have to speak about this packets of energy, so with the photoelectric effect as well as your blackbody radiation, we could say that wave or the electromagnetic nature, this one behaves, it has dual nature, isn't it? With this particular thing we could explain. So this light or this electromagnetic radiation, the concept from the above thing, we could say that it has both wave nature as well as particle nature. Now with this particular wave and particle nature, many findings, many scientists came into picture. First, the scientist who came or who could explain us about the packet of energy was Einstein. So Einstein, what did he give? In 1905, he said, or he is given as a relation between the energy of this particular quanta or the photon by capital E, energy of the photon, which is equal to h nu. H is a Planck's constant, nu. Okay, right? And now Einstein, this is not Einstein equation. Basically, this is energy of the photon. So Einstein then for this energy of the photon. So let us write this as energy of photon. Energy of photon. Then Einstein in 1905 gave an equation. It's called to E is equal to mc square. right? So energy is h nu, packet of quanta of energy, and this is E is equal to mc square, which is given by Einstein. Now let us equate this. Let us take this as equation 1. Let us take this as equation 2. Now let us relate. Now what is m? M is the mass of the photon. C is the velocity, right? So when let us equate both E and E, and equate h nu is equal to mc square. These two are done. Now I'll take this mass out. Mass is equal to h nu by c square. Okay, this is the concept. Fine. I can further h nu by c square. I can further write this concept, isn't it? I can write m is equal to h by c square into c by lambda. Why did I write this? Because nu is equal to c by lambda. So I've substituted that value here. Okay. Now, how can I write this? This c and this c gets cancelled. One c here, one c here. So m is equal to h by c lambda. Fine. So this is equation. Let us take this as the earlier one. We have two equations now. That equation 3 and let us take this as equation 3 and let us take this as equation 4. So basically two equations. Equations can be used to now I can use both the equations. So let us write both for calculate mass of photon. What are the two formulas which you can use? Always remember the first formula, m is equal to h nu by c square, which we have got from Einstein equation, is equal to h nu. The second one, I can write m is equal to h by c lambda. Both the equations I can easily use it and just calculate mass of the photon. Now, so here let us now speak about it. Now gradually I've calculated this mass of the photon. Now I have to come and understand a concept called, after de Broglie equation.